The monatomic elements got us pretty far in naming our ions, but we need to introduce a few other groups of ions so we can eventually get to the compounds. The first are our transition metal cations, and the second will be our polyatomic ions. The transition metal cations are kind of a figure it out group, while the polyatomic ions are definitely a memorize it group. Either way, more places for you to practice. Remember our periodic table that we used when we were figuring out the charges on the monatomic ions? Well, now we're going to worry about the middle of it. A number of our transition metal elements can adopt more than one oxidation state, which is kind of a fancy term for charge. In yet another instance where this will make more sense later in the term, the outermost electrons of these elements are very close in energy to the inner shell electrons, which means that they can lose different numbers of electrons depending on chemical environment and still remain stable while they do so. These different cations will behave differently, so you guessed it, they will have to be named differently as well. While you won't have to predict what charge a particular transition metal element might have most commonly, you will have to recognize those elements that can vary in charge and name them appropriately. You'll also be responsible for knowing which transition elements do not vary in charge. Not all of our transition metals can adopt more than one oxidation state. Zinc, cadmium, and silver are three of our very big distractors here. You won't apply the Roman numeral rule that we'll see in a minute with any of these guys. There will be exactly 0 times that I'll ask you to rattle off all of the possible oxidation states for any particular transition metal. Instead, you'll have to figure out what the charge on the cation is based off of the anion in the compound, which we will work on in a later video. But since students love to see things in list form, here's a relatively not worthwhile list of some of the elements that vary in oxidation state. Most of these elements have a most common oxidation state. You won't have to tell me what that is even, but know that some of the metals in this list will only exhibit some of these oxidation states in very rare instances. Know also that this list isn't complete. Remember I said it was not very worthwhile. But these are some of the elements that you can expect to see more than others come quiz time. The length of the list should say this for me, but do not try to memorize these. Let's take a minute and focus on chromium. There are 3 oxidation states listed here, though more have actually been reported for chromium. We'll figure out how many cations and how many anions will come together to form ionic compounds in a different subsection. But for now, let's look at the chlorides of chromium. Chromium 2 chloride is a white, water-stable solid. Chromium 3 chloride actually has a couple of forms. If no waters are present in the compound, it is a purple crystalline solid, or if waters are present, it is a dark green powdery compound. More commonly, the latter. Chromium 6 chloride is unstable and highly reactive. It's hard to isolate, so it's hard to describe its appearance. All of these compounds are different in appearance. They're also different in the way they react and in their toxicity. So it's important that the chemist knows which of these compounds they're dealing with so that they complete their work safely. Simply name them all chromium chloride to describe the general types of ions present is not going to do. What we do instead is name the cation and tell the chemist the charge on that cation. All 3 of these names might appear similar, but they are just different enough to give the chemist everything that they might need to complete their work. Notice that the charge on the cation is given with a capital Roman numeral right behind the name of the element. Since the charge on the chromium is 2+ in CrCl2, a capital Roman numeral 2 is used in the first compound. I've color-coded both of these with purple so that you can see how the charge and the Roman numeral correlate. In the second compound, CrCl3, the charge on the cation is 3+, so a capital Roman numeral 3 is used. And in the last compound, the charge on the cation is 6+, so a capital Roman numeral 6 is used. In short, name the element. Immediately after the element, open a set of parentheses. Include the charge as a capital Roman numeral inside of that parenthesis. Here are what might seem like small points that will end up being important to you naming all of these correctly. First, these compounds, like the molecular compounds and the type 1 cations that we saw earlier, are not going to be proper nouns unless they start a sentence. They will be keyed into Canvas in their lowercase form, and you'll be expected to input them that way as well. Second, there's no space between the name of the element and that set of parentheses. The actual formatting of the transition metal compound names is all over the place depending on where you look on the internet. But the IUPAC, which is the body that governs chemical nomenclature, states that there is no space between these two. That is what they say is correct, and we are going to do it correctly. Answers in Canvas will not have a space between the name and that set of parentheses. Keep that in mind when you're entering your answers. Our charges are going to be of 7 or less, which means that we will only need to use Roman numerals between 1 and 7. Every number in that range will use only I's or V's. Depending on the font used, it can be hard to differentiate between a capital I and a lowercase l, but never input the latter. Depending on how old school the person who taught you chemistry was before me, you might have had to learn the ich and us versions of the transition metal elements. This system is very outdated and was replaced with the Roman numeral system decades ago. We will not use the older system at all in this course. If your transition metal is on the list of those that adopt a single oxidation state, namely zinc, silver, and cadmium, then you will not use a Roman numeral with these compounds. These are often included as distractors on quizzes to see if you're paying attention. Lastly, your spelling will still matter here. We'll use the American spelling of elements in this course. Practice writing these out so that it will help you with the spelling. One last big group of pieces to name, and these are going to be the polyatomic ions. Polyatomic ions are groups of elements, usually nonmetals, though there are exceptions to this, that carry around a charge as a group. They stay together as a charged unit. Most of the time, these ions used to be a molecule, and then they gained or lost something that gives them an overall charge now. That something is usually a proton or a positively charged hydrogen. Take nitric acid, or HNO3, for instance. This is a group of covalently bonded nonmetal elements, otherwise known as a molecule. When this molecule is added to water, which is also a group of covalently bonded nonmetal elements, also known as a molecule, HNO3 will act as an acid. There's more on this in Module 3 and in 117. But know that this means it will donate its proton or that hydrogen to the water molecule. When this occurs, the water and the nitric acid no longer exist in the same form. They've been converted to the nitrate anion, or NO3-, and the hydronium cation, or H3O+. The groups of atoms here, in both of these cases, are still nonmetal elements. They're still covalently bonded to one another. That donation of the proton can't change that. So, polyatomic ions themselves exhibit covalent bonding between the atoms that remain. But those remaining atoms also carry a permanent charge now. That hydrogen ion that left the nitric acid was positively charged. So the nitrate anion that is left over now carries a negative charge distributed among those remaining atoms. Similarly, the water molecule now has an extra positive charge because it accepted that same proton that left the acid. So the hydronium ion as a whole is now a cation, and all 4 atoms associated with the hydronium ion share that 1+ charge. These newly formed polyatomic ions can go out into their chemical world and form ionic compounds with other oppositely charged ions. Though, truth be told, the hydronium ion doesn't really do this very often. The rest of the ions in your table definitely do, though. When they form compounds, there will be a transfer of charge between the whole polyatomic ion group and whatever it is interacting with. So there's an ionic interaction between the polyatomic ion and its counter ion. Hopefully you've caught on to the fact that I have defined polyatomic ions as both covalently bonded and exhibiting ionic interactions. This will always be the case whenever you see an ionic compound that contains a polyatomic ion. Know that you won't have to draw molecular stories like this one for me come quiz time. Your big job with polyatomic ions is to ensure that you can rattle off their names and formulas, including the appropriate charge. There's a very large table in the content page that you're responsible for. I've organized these as I learned them, which is by charge. You are welcome to organize them in whatever manner you think will work best for you, but you will have to effort here to get all of these memorized before your quiz is due. But once you know their names, formulas, and charges, using these polyatomic ions is just like using any other ion on the periodic table. So now we know most of the pieces to our ionic nomenclature puzzle. We've added the transition metal ions, which can vary in oxidation state, so they require their own set of nomenclature rules. You'll need to be familiar with the Roman numerals and the number of very picky things that go into naming these cations. We'll work on forming these compounds in the next section. The last big group, and these are where I cannot encourage you strongly enough to get started with the memorizing, are our polyatomic ions. Brute force these guys out. Lots of flashcards, angry yelling at group mates when you see them in Blazer Hall, anything it takes to get these down.